There, it's going. Okay. Yes. So I went into Cracker Barrel, and you guys probably know where I'm going with this, right? What do they have at every table in Cracker Barrel? Well, peg game. How many people have beat the peg game? How many times did it take you to beat the peg game? Several times. And I was trying to figure out why it was such a difficult thing to beat this peg game, and then I programmed it because I was tired of me losing all the time. And so I started out, and I've got the applet somewhere. I did this in Java years and years ago. But I did it really to cheat because I wanted to go out to a job interview, and if they took me to this place, I wanted to say, oh, well, that's very interesting, and not even really look at the board and just kind of know ahead of time how to win the game, regardless of the configuration. One thing that I noticed is that after you move the first peg, your chances of winning go down to about 12%. Okay? And that's the problem, right? Because there's so few paths that are going through this that I think it gets down to 4 and 2 and all these different kind of percentages at certain points. So choosing the first move is going to help. But how is the computer doing this? By the way, there are 14,700 something different ways to win the game and 200 and something thousand ways to lose. Because I played all the games. I told the computer just to do them all. So how does it do it? It's recursion, believe it or not. Okay, so what you do if you were going to have a checkers game or a tic-tac-toe game or something like that, what happens, and you don't know what recursion is, that's cool, but assume that you have a starting state, right, which is the board in the initial configuration. Then what happens? The computer plays one ply down. Now, this is a lot different than the recursion that we've probably studied that goes depth and everything else, but it says, okay, fine, I'm going to do all of the next available moves. Then what happens? It's going to then predict, okay, here's all the next possible sets that you could do, and then what's next? Next possible sets that I could do, and so on and so forth. And it can only go down so far. Why? Because think about how much memory you're eating up when you do these kinds of things. Yeah, a whole bunch. So why is tic-tac-toe so easy then? How tall is your stack, right? You can only go down 9 deep. You really don't have a lot of options there. What about chess? Think about it. You could move a bishop back and forth and back and forth and back and forth. So how many different chess games are there? An infinite number of chess games, right? So that's one of the problems that computing had based off of intelligence and everything else. And so we're not going to go down that path, but that's generally how to make these artificial intelligence things. So I coded this thing up, and I could not beat my own chess program. So what does that make me?
A genius.
A stupid genius? Are computers smart then? That's the question. No, they are not smart. What can they do? They're just fast. That's all they can do is they can play a whole bunch of different versions of the game out. They can only go down so far given the amount of time that it takes to generate that and the amount of memory that they have. So it's not that computers are smart, it's that they're fast. So you can take advantage of those kinds of things to get realistic intelligence. Now, when we talk about artificial intelligence in this class, we're really not going to be talking about the traditional artificial intelligence class that you guys have to take. Everybody has to take that class, right? It's a required class. Okay, so I'll leave that for a later exercise. It's a great exercise for you to go into. So we'll start talking about all of the fun, different kinds of artificial intelligence. Whoa, let's cancel that. Slideshow from current slide. You guys are still angry at me about the exam, but it's okay. I'm just fine. If you've seen your grade, again, you're going to dwell on that. Don't beat yourself up too much. And I'm not looking at anybody. I don't know who made what. I don't keep track.
Where's the grade posted?
It's in D2L.
And it's under grades? Or?
Should be available under grades, right. Right. And you can calculate where you stand. And if you want to see the grade that I've calculated for you, you just send me an email, and I'll let you know how I broke that down. You should be able to do it on your own, but if not, that's okay. All right, so when we get into artificial intelligence, one of the things that we're trying to do is to simulate being a human. You probably have seen iRobot and all of these kinds of things. This is a very deep philosophical, theological kind of question. Are we ever going to have robotics that approximate the human mind?
Possibly.
Maybe. You are right, maybe. Who knows? In my personal opinion, I don't believe so. I think that the human brain and the way that we're structured is so complex that they're not going to be able to approximate it. And I base that actually in mathematics. Mathematics says there's a whole class of problems called NP-complete problems. I believe we are NP-complete. If that makes sense, then great. And if not, it doesn't really matter. Okay? So, what's that?
I'll look it up.
It's called non-deterministic polynomial time algorithms. And you'll study that when you take an algorithms class, if you take an algorithms class. Okay, so basically what that means is that the problem becomes so vast that computers can't solve it, at least in the current implementation that we have. Even when we make that jump into quantum computing, I don't know if it's really possible. Can you teach a computer to paint art in a meaningful way and to have emotions, and then how does that tie in with human beings, and all sorts of stuff like that we're not going to get into, right? That's not what this lecture is about. So AI describes the intelligence embodied in any manufactured device. That's, again, straight from the chapter 5.3 that everybody read before they came to class. I'm sure you've seen that. We need AI both for enemies and for allies. So we need to structure these things in intelligent ways and to try to approximate intelligence in the game. Now, what does that really mean? There's a couple of implications. It has to be intelligent but purposely flawed. Why? Here's what I don't want you to do. It's very easy. I say very easy. It's way easy to make artificial intelligence that's too good. Have you ever played a game that you just can't win? Yeah. And I'm talking about, it doesn't matter. It's Mario. It could be any 2D, 3D game. Why is it so good?
The programmers are lazy.
It's scaling.
It knows too much.
It knows too much. We actually have to cripple what the computer knows to give any kind of meaningful artificial intelligence, which is a surprise. Because think about what is it that the computer knows?
Everything.
It knows, well, it doesn't know everything,
Everything about the game.
it knows everything about the game. It knows where the player is, how fast the player is going, their fuel consumption. It knows how many bullets they have left. It has all of the state of the game at its disposal. Could it abuse that power?
Yes.
Have you ever thought that the computer has abused that power when you're playing the game?
Yes. Maybe.
And question, how on earth could they know when I was playing StarCraft that this thing was way over there? When no, there's no scouts over there. The game clearly cheated. Okay, I still think StarCraft cheats. That's my opinion.
High difficulty.
At the higher levels, I absolutely believe that it cheats. And that's fine, but you better let the user know that. You better let the player know that, hey, we're going to cheat. Otherwise, they're going to be mad, right? And there's going to be frustration. You don't want a frustrated player. All right, so opponents have to present some kind of challenge. You have to keep the game fun. That's the main idea. You must lose to the player in a fun manner. These are the overarching design things that we have to keep in mind as we're designing our artificial intelligence. If you make your artificial intelligence too difficult, nobody's going to play the game. Again, we don't want to be the designer from hell. Keep that in mind. Okay? AI also has to have no intended weaknesses. In other words, you shouldn't be able to use this formulaic approach to beating the boss enemy every single time. Have you done that before?
Yeah. Oh, yeah. That's in almost every single game for every boss.
It is, but now they've made it where there are patterns to the boss. So once you figure out the pattern, then you can take down the boss, right? But there's also ways to abuse the system so that there are these intended kind of weaknesses that are there. So you try to avoid those. Examples could be in some of the earlier games where they didn't think things through. Oh, if I just hide here in the corner, I can sit there and shoot and shoot and shoot and ricochet off the wall, and the thing never comes to get me, right? You've all done this kind of thing where you found these flaws that were there that should not have been. Okay, so that's what we're talking about. I'm sorry?
Part of the fun of the game. Rick.
So to show you what we're talking about there, have you ever seen the snake game, the worm game, anything? You've got a body that grows over time. Yeah. My son had to play this as part of his school. Well, he found out that if you go off the side of the screen, it brings you back around to the other side. So what he did, and I was not upset, I was actually proud that he figured this out. So he made it where he would go off the side of the screen at a slight angle. So what would happen is the body would keep growing and growing and growing, and it would actually consume the entire screen, the body of this snake, and he was supposed to be eating these ships on the water and stuff like that. And I was like, that's my boy. He's cheated, but it's like, well, at least he figured it out. So, but anyway, yeah, so the AI has to not fail or appear dumb, because otherwise they're going to think that there's no challenge that's really there, and the illusion of artificial intelligence is going to go away. So we have to perform artificial intelligence within the constraints of a real-time system, right? We know that we have that issue with graphics, and we can push a certain number of polygons, but realize that on most systems, the artificial intelligence only receives between 10 and 20% of the overall CPU time. What does that imply? You can't use all of these fancy neural networks and these other kinds of advanced artificial intelligence to run through your characters. You don't have that much time to devote to super intelligent beings. They have to be quick, they have to make real knee-jerk reactions, and then they have to come across as intelligent as possible. So AI also has to be configurable, right? So designers can adjust the difficulty. Let me show you something. I've had to work on an AI system. I am not an artificial intelligence guru, so please don't read this way. But one of the things that I did is I had to write an AI engine. And so what I did is I said, fine, AI engine, pointer, engine, gets a new, that says new in some language, AI 1. Okay? What are we talking about here? A little bit later on, engine gets a new AI 2. What are we doing? No, this is not component-based. Good try. What do we call that? Programming. What is it?
Polymorphism.
Polymorphism. So if you make all of this stuff work, think about it. All I have to do is swap in a new artificial intelligence engine to get the robot or whatever kind of enemy you have to fight to be a little bit smarter. So we can start to do these kinds of things. The AI has to be configurable because I didn't want some game designer to say, okay, now I'm going to have to dive into the guts of the artificial intelligence. No. You say what level you want it to be, and then we can pop in new artificial intelligence engines as needed. Okay? Also, the AI has to hit the shipping date. One of the things that a lot of people, you get excited about artificial intelligence. How many people think artificial intelligence is cool and you want to see little characters running around? Everybody likes to see that, right? As soon as you propose something new, what's the danger? This has never been done before. Artificial intelligence is amazing.
Nobody's going to know how to fix it if you don't do it right.
How about this? You may not finish. Think about it, because you're proposing something new, never been done. Well, it's never been done, so nobody has any idea how long that's going to take to do. Right? So you can say all these kinds of things, but there is a shipping date. It's written down in the design doc at the very beginning. This is the shipping date. This is what we have to hit. You have all these crunch time nasty periods. You guys know that if you went to the game jam, you have a date and you have to hit it, right? Same kind of thing. All right? We talked about this also. AI has perfect data, but the goal is not to have perfect AI. And I'll show you a couple of examples of this. Perfect AI is no fun and expensive to compute, and the goal is to basically to have fun. Watch what we could do. If you're really nasty, let's say that we're writing asteroids or something like that. Doesn't really matter. Here's your ship. Here is, let's say, the enemy ship, and I'll just write an X right there. The enemy knows that you're going this fast, right? You have a velocity associated with your ship. You have a certain bullet count. You have all that kind of stuff. What if this thing we're going to shoot, where should it shoot? It knows that at a particular time you're going to be right here because all it has to do is multiply your velocity times the number of frames that it wants to leap forward to, and it can shoot out here. You ever seen this? You ever fight a bully mong? What do bully mongs do? They throw rocks at where you're going to be. That's uncomfortable for a lot of folks, and they get hit a lot by rocks. So what do? You go over like that, and then you take a step back, and then it flies off to the side, right? But these are the artificial intelligence kinds of things that you can leverage because they're not hard to program. Okay? If you want to get into artificial intelligence and that's your thing, how many people would be on a typical team? On all of these major productions, you would have probably 3 AI folks that are doing all of the programming, all of the artificial intelligence for a full-blown multi-million dollar AAA title. What does that imply? You have to be really good to get into the artificial. Everybody wants to get into this. It is cool. In fact, I think there's a requirement in your final project that you have some AI, right? What is that AI going to look like? It's going to be simple. You may have a sidekick that follows you around. Look at that. Hey, the sidekick follows me around. Or look at this. The enemy comes towards me, and it doesn't get stuck on a wall. Something like that. It doesn't really matter.
That's smart pathfinding.
I don't even know if I would require you to do pathfinding. I would even keep it easier than that. Okay? Did that just change twice? No. Okay. So if you're going to write a game agent, let's talk about some of the agents that are out there. These would be NPCs, which are non-player characters. So there's a couple of different things. If you've ever played any of these, well, I hate to say war games, but you go up on a camp, you see a whole bunch of enemies that are patrolling across there. Have you ever shot and then seen all of them instantly just run? Like as soon as you press the trigger, the second that you press the trigger, somehow they magically moved out of the way so they didn't get hit. You ever seen this?
Yeah.
Right? No? You ever seen it where you snipe somebody from really, really far away and then everybody activates over there?
Yeah.
Okay? Is this how humans work? No. If you've got somebody that's over there and they're standing in the guard tower or something like that, you take them out and then everybody else is going to scramble. No, that's not the way that it really works. It starts with sensing, okay? So we have to cripple the AI to say we're going to limit what they can see because they do have access to everything that's available, but we're going to limit it to have vision that's limited. They can only see so far. They don't have elven eyes where they can see out there. The hearing is also distant, so if you have shots fired and things like that, it has a fade off. Communication with other agents. What's the problem here?
Communication.
They're all like one sentient being.
They're all one sentient being. You've all seen this before where they all just instantly are, oh, okay, everybody's aware and they're all...
Someone's attacked the hives.
It's something like that. But they instantly know what is going on in the game, and you don't want this. You want there to be a spreading time if you have a group of things that you're taking on. Okay? So the reaction time, we had already talked about this. You have to delay them a bit because otherwise it looks very robotic. Other things that go on. Step 2 would be the thinking phase. We had talked about this before, but you might do something like a searching algorithm. We're going to talk about a couple of searching algorithms. This could be, okay, if I've heard the shot that's been fired, I've sensed that, now it's time for me to go over and engage with the player, something like that. So there's a couple different things that we're going to see in just a minute. Machine learning is not often used. This would be neural networks and such. Also, here's a problem. You have to be aware of it. It's a case called flip-flopping. What do you suppose that is?
Get stuck between.
It's like, oh gosh, there's a giant beast over there. I better get away because I'm too close. So now, next frame, you're over here. Now what?
Far away. I wasn't moving towards there.
Yeah, there's a giant beast, but I'm okay. So maybe I'll patrol back over here because I'm on my patrol. And then, oh my gosh, next frame, I'm too close to the snow beast. So what I'm going to do, get over here. Now I'm in patrol, and I go right back in. So what's going to happen? Every frame, you're going to be toggling back and forth. So you have to be aware of situations like that. Basically, what you have to do is to commit your character to say, this is the current state that I'm in, and until a sufficient amount of time has passed, I'm not going to go back to another state. All right, so you want to avoid these flip-flopping kind of situations. Third thing is acting. So if you have an intelligent NPC, the user has to see and hear intelligent things. Now, there's very subtle things that you can do that are not directly AI. But, for example, if the agent knows it's going to die, you just shot him in the leg or something like that. It doesn't really matter. What would you expect to happen if that really occurred in real life? You would scream. Why is that such a big deal? Because you're trying to convey that this is actually an intelligent being. So you can start to integrate these human things that are not necessarily AI, but if it screams knowing that it's going to die, it's like, I'm going to die, how could you do this to me? It's going to seem more intelligent. You can get those things for free where it's not just extra code. Okay? So it should scream to show that it's actually comprehending what's going on. Okay? Other things that you could do, learning and remembering. Hey, last time I was there, I died. This is not a good spot to go to. So what could happen?
Avoid that spot.
You could avoid that spot. You could avoid doing the last thing that you did that got you killed. So real simple kinds of things. Yes?
I remember reading a thread online about Quake, or one of the Quake games, where this guy set up a server and let like the AI run on there. Like for you. Oh, it was fake?
Yeah,
okay, well, screw that.
Apparently the AI stopped fighting each other because they thought that was perfect.
Well, in Borderlands, they fight each other.
Yeah.
I keep going back to Borderlands. But and I also know that I played a whole lot of Quake to the point where I'd watch these competitions of the virtual thing, and it was country against country, and eventually Japan and the United States were playing. And I don't know who, I can't remember what the guy's name was, but he was so good, he knew where all the spawn points for the armor and everything else was. The final score was something like 135 to -1. And the reason the -1 is because the other guy fell into the lava. That's the only thing I really know about Quake other than... Okay.
That's pretty impressive.
It's very impressive, yes, which is why I will not be competing. We had talked about this also, about it's very easy to make AI too difficult, so we have to basically dumb it down a little bit. We talked about agent cheating, so I'm just going to skip over that. That's when you're abusing the system. Okay, now how are you going to implement this? This is really the core of what I want you to learn from a programming piece. There are things called finite state machines. Have you heard of these before? A lot of you have. If you haven't taken the theory of computation, then you'll see these things a bit later on. But this is how most AI in games is written. Okay, so you have your character that's in a particular state, and I'm going to show you a code example here in just a second. But the basic idea is that we're going to change from state to state based on the input, the state of the game, everything that's going on with regard to the environment that's around this character. Okay? So there's a lot of benefits to it. In fact, I'm just going to skip straight to this. Here's an example of what a very simple finite state machine would be. It's a light switch. Okay? So you have these two different states. What states can a light bulb be in? On and off, right? So that's pretty straightforward. So what happens if I flip the switch down? It's going to go from on to off. And then if I flip it the other way, it's going to go to the on state. So you can see that we have an input, which is the state of the switch. And then we have two different states that the light bulb can be. Does that make sense? Now, what different states might an NPC be in? Let's say it's a nasty guy. It's an enemy.
Patrol.
Patrol. What else could they do?
Attack.
They could be attacking. Yes. What else?
Running away.
Running away. Fear. That's it. Pretty straightforward things. Well, I think you picked up on most of them. Here you go. Here's some code. You want to see what this looks like, right? Don't worry about what an enumeration is. You know what? Do worry about it. You need to know those things. Here's a function that takes in an int pointer. Notice there's nothing really complex. Does it have to be a pointer? No, it doesn't. So keep going with me here. We're going to switch on the state, and if the case is wander, notice that's one of our enumerations up there. It's actually a 0. You want to think of it that way, okay? So if the case is wander, then what do? We wander. What might wander be? It's another function, but what's going to happen? You're going to change your position a little bit. Maybe you're updating your animation, something like that, okay? If you see an enemy, whatever code that is, it could be that you're close, doesn't really matter, then we're going to change the state to attack. And then break. What happens in the break? It's going to kick me out of this. In the next frame, we're going to be in the attack mode. So what's going to happen? Right? So we switch on the state. The state's now attack. This is now false. We're not wandering, so we're going to attack. So what do? Attack. What might attack be?
Shoot.
Okay. What else might it be? It could be shoot, yes.
Stab.
Probably face and go in the direction of the thing that you're trying to attack. It could be a punching game, something like that. If you're low on health, what's going to happen?
Flee.
You're going to change your state to flee. If there's no enemy, and you are currently in attack, and let's say that the enemy is dead, what's going to happen? We're going to change our state back to wander. Okay? And then finally right here, in the case of flee, flee is going to probably run away from the character. If no enemy, then what are we going to do? Go back to the wander state. So you can see that we only have 3 states, and depending on if we're low on health or any of these other kind of situations, we're going to change the state that we're in. That's it. You're going to be blown away at all of the major games that are out there that use something as simple as this, and they're full-blown AAA title kind of stuff. You can do some pretty amazing things with even 3 states like this, and it looks reasonable. Comments, questions about that? Does that make sense? Okay, yes?
I remember taking a software engineering class saying to avoid switch case statements because they were bad, and that's all it said in the textbook was that they were bad. The teacher didn't even know why. Do you know why?
Because they're bad. If you don't know that by now. Is there anybody that knows the answer to that? I don't.
You're supposed to use try catch and consider statements. I don't think.
Yeah, but try catch is something different. It's basically switch versus if else's. Yes.
Some switch statements only accept primitive data types. So if you have objects, you can't really.
That's true. So like strings and things like that. Yes. Anything else? No other discussion on that. I don't know. To me, it would depend on how the compiler implemented that to begin with, because underneath it all goes down to a different form anyway. So, okay. So here's some common AI that you probably will encounter at some point. A-star path planning is the #1 thing that gamers usually talk about. What is A-star path planning? It is a path planning algorithm, which means what? Yeah, it's going to go from point A to point B in the most intelligent way possible. Okay. We have behavior trees. I'm going to skip that one because you really don't hear these things a whole lot. There's a command hierarchy, though. And a command hierarchy, you can imagine it's a lot like a military structure where you have one thing that kind of knows the high level of what needs to go on, and then they send out units, right? So you might have divisions and all these other kinds of things, and they further disseminate what the responsibility is. So eventually, yes, you would have generals, you would have corporals, you would have all of these different military positions, and then finally down here at the bottom, you'd have the privates that are the ones that are running out there. So that's a structure that you could leverage in game AI. Dead Reckoning. That's a great game. But what is it? It's a term. It's an important term. You're reading from the slide. Leading the target, yes. Why can you lead the target? Because you have perfect information. So dead reckoning says that you're going to shoot and you're always going to kill. You ever seen bots try to take on a bot and you always die?
Yep.
Why? Because they're perfect. They have dead reckoning. They're going to predict where you're going to be. Okay, emergent behavior. You probably will see this later tonight when you're working on your flocking. Somebody said, hey, why am I getting this bizarro behavior? That's emergent behavior. Emergent behavior is cool. It's like, hey, I didn't know that it would really do that. And you start to get all these weird kinds of things. That ties directly in with flocking. We know that flocking is the movement of groups, and a couple of different ways that you can structure this. You can have swarming, you can have flocking, you can have any number of things. But we have separation, alignment towards the average heading of a flock, and steer towards average position of the flock. What I'm trying to convey here is that you have 3 different vectors. Everybody pay attention. If you have not done the assignment, this is the important key thing. You have 3 different vectors that you have to worry about. What are they? Okay, well, each void, each bird or whatever you want to call it, has a position. It also has a velocity, yes? Okay? So the question is, what is the velocity, how much is the velocity going to change by? It's going to be changed by 3 different things. What are they?
The avoidance vector.
The avoidance vector, which means what?
How far away am I from the guy's next?
Okay, so when you're trying to calculate this avoidance vector, what do you have to do?
You have to scan every other.
You have to scan everything, every other void that's in this system, and if they're close enough, what do you need to do?
Change your vector.
Add to the avoidance.
You want to go exactly the opposite direction. So what's going to happen in this first phase as you go through this separation phase is that you're looking at everything and you're going the opposite direction and you're summing all of these things up. And you're going to get an average heading to get away from all of these things that you could potentially collide with. And what happens is as your creatures are coming in, when you see them, then they immediately turn in other directions and stuff. That's the avoidance vector. That's the separation vector. The next one is the average the average heading of the flock. What's happening here? You've watched birds fly, right?
Mm-hmm.
Do they go out in all different directions?
No.
What do they do?
They're heading to the same place.
Sometimes they go out to the outside, but what do? They eventually come back in because they want to be in the middle of this group, right? But if they get too close, what are they going to do? They're going to separate back out. So we have this thing that's trying to pull them in back together again. This is a very light vector, right? If we have assigned weights, the separation vector says, I need to get the heck away because I'm about to hit another bird. The alignment towards the average heading is a weak vector that's trying to pull things back in together, okay? And then steer towards the average position of the flock lead. I think we just talked about that. Oh, this is the average heading of the flock, which means if all the other birds are going this way, which way should I go?
That way.
That way, right? So there's a couple of different things. What are we going to replace this one by? Where the player is, right? So you have to figure out a couple different things, and I think it walks you through that in the assignment. All right. Also, I'll go ahead and tell this to you. There is a 1302 lab that walks you through this. That would be a good starting point. Everybody go back to my previous semesters. Find the lab before you do anything else. Yes, read the assignment first. Go back and look at the lab because that will definitely help you. I shouldn't say that because it gives you starting code, and I'm trying to encourage you to code, but there you go. Okay.
So what about the, well, can I bring up the issue that I was having with my code where it seemed like essentially when I would have voids in the center of the group, occasionally what would happen is sometimes they seem to get like pushed together to where like they're almost right on top of each other, and the avoidance vector doesn't seem to be working properly. But I'm thinking it might be because it's essentially surrounded by other voids.
It could be. So look at it this way. The voids that are in the middle are kind of screwed, right? Because where do they go? They go this way. But wait, there's another one there. And there's, so they have to kind of, what should happen is that the ones that are on the outside should be repelled away from that. And you should see this initial kind of explosion that occurs. And then once they get far enough out, then they try to come back in. But what I would do is I would weight the avoidance vector heavier because we're summing up all of these vectors trying to figure out what our new velocity is going to be for that void. You're going to have weird stuff happen. I'll go ahead and tell you. You're going to see voids that just shoot off the screen, and they're gone, and you will never see them again. Has anybody seen this yet? Okay, yes, it will happen probably, and it's kind of funny and it's kind of cool. If anything, please turn something in. Okay, it's due. I think I said it at 8 a.m. tomorrow morning, something like this. Please turn something in. I can't overemphasize that. Here you go. That's in the lab. I'm going to skip over that. How are we doing on time? You got it. Okay, we've got time. All right, common game AI. There's also influence mapping. This is usually has to do with the amount of materials and resources that you have laid out in a 2D grid. So you might naturally know that, hey, there's a whole bunch of gold over here, so there's influence that has associated with it. This could also be good for path planning if you know that there's a lot of sand over here that's easy to walk across, or swamp or something that's not easy to walk across. That can have influence too. Okay? There's also some interesting things here, and you might have seen this before. Level of detail AI. Now, when we're talking about level of detail, what are we talking about? Don't say the amount of detail. Yes, I get that. Have you ever played an MMORPG, something like that, and you see characters that are really far away, and they pop, they're right here, and then they pop over here, and then they pop over here, and they do all that kind of stuff? Does anybody know why that happens?
It's pointless to give them an AI when they're really far away.
Well, it could be an actual another player. Let's say it's a live person that's in this MMORPG, and you see them, and they're running across the field really far away, and all of a sudden they'll just teleport. They'll be over here, and then all of a sudden they just kind of teleport, and they're over here. Does anybody know why that happens? It's not lag, interestingly enough. What happens is this whole level of detail can be applied to just about anything. You can have level of detail for meshes, things that are further away. Do you need as much detail? No. So that's true across everything. So even in networking, how often do I need to see the updates of the character that's like 2 miles way over there? Not a whole lot. But as that character gets closer, what's going to happen? I need more detail. I need more resolution on where they're updates. And so that same thing is going on with AI. Things that are really far away, they can be as dumb as a brick, right? They can sit there and eat mud for all you care, right? But as they get closer, you might want to spend more time in the AI engine aspect, right? So you run a different kind of code. Okay, there's, skip over this next one. We'll come back to that. Obstacle avoidance. You shouldn't run into trash cans. Your character shouldn't run into trash cans as they're going around that. We'll talk about obstacle avoidance in just a second. And then also things like terrain analysis, identifying strategic locations ties into it as well. So these are just all common kinds of things that you would see in games. Yes?
What is it if you're, say you're playing a game and you see a character or whatever it acts normally does, and then you come back later and it just is walking into a wall or something like that?
That would be bad programming. Yeah, characters that walk into walls and they just keep doing that, that usually means there's a screw-up.
But let's say, like I said earlier, they were doing everything wrong.
Again, I would attribute it to bad programming. It's got to be a bug in the system. It thinks it's probably somewhere that it's not, I would imagine. Okay, so when we get into path planning, and this is building up to our understanding of this thing called A-star. We're not going to get into all the details. You can find it out on Wikipedia. But let's look at this. If we had a 2D terrain, something like this, this is a common setup for a lot of 2D games. That you would have a grid, and you would have certain attributes associated with each cell that's inside this grid. What are some of those attributes? Well, you might have seen this in a Legend of Zelda kind of lab. There are certain things that you can't pass through. They're not passable. There are certain features of this. Hey, how hard is it to walk through trees versus walking through, let's say, a road or something like that? So you can assign all of these different attributes to the different grid pieces, but basically each cell is going to be marked as either passable or not, or something in between, right? So how can you pass through swamp? Yeah. You can, but it's slow. So we can start to take all of those things into consideration. But again, everything is organized as this grid. Okay? You ever heard of waypoints?
Yeah.
What are they?
They're safe waypoints.
Well, not when it comes to artificial intelligence, okay? Waypoint graphs are basically lines that you can walk on. And you've probably seen this if you have characters of ogres or something that are coming along, they'll follow a path. And if you see it's really poor, what's going to happen is they'll go from point A to point B, and they'll do it in an exact straight line. What's the problem with that? They're all marching in formation on this exact line, and it looks kind of goofy. How could you solve that problem? Flocking. Right? You don't want them to be, you want them kind of cluster, and they can do all this kind of thing, and they'll come back towards the group as they need. But anyway, so waypoint graphs are basically, they're going to walk from point A to point B, and these are going to be straight lines, even though they could be something like Bézier's. You guys have heard of Bézier's, right? Yeah. Okay. Okay, another thing that you're going to see, and this is really popular in Unity, are nav meshes. So when you get into the 3D terrain aspect, it's going to say, do you want to construct a nav mesh? And it'll visualize what the nav mesh is. Now, what is the nav mesh? Basically, it's the area that you can walk on. And it's fairly simple to construct, because if an edge isn't shared, you can't go over it. I want you to convince yourself of that right now. Look up here. You see the edges? If they're not shared across two different polygons, what do you know?
There's a wall.
If you go over that, you're going to die. right? So any of these things right here, this edge right there isn't shared, this one's not shared. None of these guys on the outside are shared. Therefore, you know you've reached the end of the world with regard to this particular area that you're in. Make sense? So constructing a nav mesh is not something that you will have to do. That's something that the game engine does, but it's still a theory that we use all the time. Somebody had a comment?
It's a proverbial invisible wall.
Yeah, but you know that you don't want to take another step, because if you do, you're going to fall off the edge of the
Oh,
world.
so it can actually fall off.
Oh, sure.
Awesome.
I mean, you guys have probably written these things where you've fallen off the edge of the screen, right?
Yep.
Yeah, it happens all the time. Okay? We also have random trace algorithms. You move towards the goal, then trace around the obstacle. Any problems with this? Which way do you go? You go clockwise or you go counterclockwise?
Depends.
I think I can give you a situation for both of these that would be non-optimal, right? Okay? Do I need to draw it out? We're right here. This is us. We're happy smiley face. And here's where I want to go. Which way do I go? Clockwise, counterclockwise? Why? It's way shorter. So you can't always say, I'm just going to go counterclockwise, something like that, because that could lead you down the totally wrong path. I can make that even more obnoxious, but I'm not going to. Okay? So with the fundamentals, each cell, of course, has a position. It has a pointer to another cell. And here's the main idea. If you have to do the last path planing assignment 7, pay attention to this. In fact, I'm just going to visualize this. Let's go straight to it. Okay? We're going to get right into the different searches that you can use. The first one's going to be a breadth-first search. Have you ever heard of this?
Yes.
Okay? This one you can do using recursion, but you have to keep lists of things that you still have yet to visit. Okay? So watch what's going to happen. And there's a visualization that I just ripped off of realtimecollisiondetection.net. Everybody goes there, I know. But anyway, it says pi by pi. What are we really doing here? Well, if I wanted to start right here at S in this gray maze kind of thing, where do I go? What are the first options that I have? Okay, so right now I have an open and a closed list. The closed list says I've already visited. The open says, hey, these are potential kinds of things that I want to visit. So what am I going to do? I'm going to start here at S and I'm going to look up. Can I go up? No, I can't. So can I go left? Yes. I'm going to throw that in the open list. You must pay attention here. This is going to be a lifesaver, trust me. Okay? So I say I'm starting here at S. Right now I need to know where I'm going to explore. So I look around me and I say I can go left, I can go down, and I can go right. So I put them in my open list. So everybody see step 1. What do you suppose step 2 is? Okay, so for each thing that's in the open list, what am I going to do? The same thing. So if you look right here, we put the left one in first. You see, I'm on this left one. So what am I going to do? I'm going to look up, down, left, and then right. But I've already visited this spot. So I've got all of these 2s that are right there. What about this one right here? I've already added that to the open list. I've already added this to the open list. So then I go to the right one. And what I'm going to do, look up, that's a new one, and look right, and that's a new one. So do you see what's going on? If you were going to implement this, what data structures might you use? What's that? You could use a tree.
A list.
Yeah, list. Okay, you could do it. The point being is that you have to keep this notion of these are the places that I've been. These are the open and the closed. Now look at the behavior over here. You can see when we start out, it's going to go out in this kind of going in all different directions. Is there a problem with going in all different directions?
Very times.
We started down here. Where do I want to go? To this green dot that you see in the upper right. So what's the problem? It starts to grow. It starts to get really big. And think about it. Any effort going down to the left is wasted effort. I'm going in the wrong direction. So what could we do?
Heuristics.
We could do the best first approach. How do you suppose this works?
Check and see which tile is closest to your destination, and then look for all the tiles around
It's
that.
kind of the same thing. I look around. Here's the starting here in this kind of, what color is that? Okay, it's red. Fine. Salmon. Who said salmon? Okay, it's mauve or whatever. Okay, so anyway, I do the same thing. I look in all 4 different directions. I look north, south, east, west, and I add those to the open list. But which one do I process first? The one that's closest. Okay, so remember when we're talking about adding all of these kinds of things. So I say, fine, I'm going to look at everything that's surrounding the right one, and then add those things to the open list and process those first. Whatever's closest is going to be the one that I process. Any problems with this? I'll show it to you. It may not be obvious. Okay, here's breadth first on the left, and here's best first on the right. I know what you're saying. Hey, that was really stupid to do the breadth first. Well, you'd never do that. Well, guess what? It outperformed it here. Why? You see what's going on? Look at this graphic. It's a great graphic.
There are more spaces that have been checked over there, and there are fewer spaces.
But it's a
Yeah, but that one goes in like
But look at it. Remember, it's applies.
One of them's
You're half right, half wrong there. But yeah, I'm glad you're looking at that. He's saying basically the total area here is greater. So maybe the number of checks overall isn't as bad. But what did we do with the best first? We started going down here saying, look, this is the closest, this is the closest, this is the closest, and it led us down this path so we really couldn't see out there in the future. So what did we have to do? We had to start backtracking and say, is there anything closer, and eventually we found our way around and we did the best first again. Okay? So there are problems with that. There's also something called Dijkstra. This you'll learn a lot more about when you get into algorithms. The main concept here is that we have costs associated to get to each tile. So as I start to go out, I'm going to say the one that's really closest, it took me 1 unit of time to get here. As I go out another ply, it took me 2 units of time to get there, and so on and so forth, and we can change that later. Because we might find some really fast path around that didn't cost as much, and we're going to reduce the amount of time that it took to get to certain nodes that are in this thing. Okay? Does that make sense? So we're starting to relax. It's called relaxation in algorithms terms. But that's what we're doing here. Okay? Now, with A star, it combines the best first and Dijkstra together. Okay? So what you need to see is, okay, there's a heuristic cost associated with it, a lot like the best first, and then there's also a weight, an amount of time that it took me to get to a particular cell. And all you're doing is you're balancing between those two things, giving more weight to one and less weight to the other until it works out correctly. But the cool thing about this is we can now say, okay, it takes a lot of time to go through swamp. It takes a lot of time to go through mountains, but it doesn't take nearly as much time to go through a field. And that's why A star is so valuable. And I think here's an example of what it looks like. You can see there's the best first, right? And here's where the breadth first takes over, the Dijkstra part. And then you're going to see best first take over again here in just a second once it makes it around the corner. Watch. Wait for it. It'll run again. Watch it again. It does the best first, going from the start, goes straight here, and then it starts to search its way out. So it's really just a combination of the previous two things that we had seen.
So this is A star?
This is A star running, yes. But you can see once it's able to, and it makes its way around that corner, it goes back to the best first. Yes?
Who came up with this, the algorithm for this?
A star did. I should probably know that. I really don't know. It's cool, though. Okay? This is what... I guess here's somebody knocking. This is what's commonly used in games. This is the number one thing that you're going to see out there. I would recommend later on in life, I don't think it's required for everybody to do this, but that assignment 7 says, hey, let's make an A star together, I think. Look at that algorithm. It's not that long. It's probably 15, 20 lines of code, something like that. A little bit complex, but it still uses this notion of open and closed lists that we talked about. That's why that's so important. Open and closed lists. You must understand open and closed lists if you're going to understand these pathfinding kinds of things, right? Because remember, the open list says these are the things that I still have yet to explore. You can think of them as they're on the horizon of the unknown, and the closed list says that we've already been there. All right. In fact, there's the code. I'm not going to, you can't even read that, so it doesn't matter. That's it. So, where do we stand? You're going to do that assignment with a tree. Okay, so there's a challenge that's been...
Assignment with a what?
Don't ask. Seriously, what kind of questions do you have? I want to point out a couple of things just real quick before you take off. Looking at this, you're probably at this point feeling somewhat overwhelmed with the course. That's natural, right? There's a lot of stuff. Remember, the first day I said it's like every week there's something due of you. I want you to notice what's happening, though, with the schedule. As we look down the right-hand side, you can see, yeah, the flocking thing is due basically tomorrow morning, 8 a.m. kind of thing, right? Then we get into 3D graphics. You will be well prepared for this because we're going to recode some things, and I'm going to show you how to work with the camera matrix a little bit in class. Okay? Alpha game. What's supposed to be in your alpha game prototype?
Working gameplay.
Yeah, your basic mechanics are in place. Should you have a completed level? No. Should you be able to do all of the things that your character is going to rely on level 1? Yes. Okay, so if you have a freeze ray and a fire ray or something like that, and those are crucial to your game, they need to be implemented. Okay? Is it supposed to have perfect play? No, it's not supposed to have any of that kind of stuff. The reason I'm pointing this out is because this is a huge portion of it's 30%, right? Your final project is 30%. IK is the last assignment. This one's going to be tricky. I'm going to try to prepare you. I'm going to rewrite the assignment to better prepare you for this, and we're going to talk about it in class. Okay? I wouldn't start this one yet. Okay? Then, what comes up?
Lots of milestones.
That's a milestone.
Milestone. What are those milestones?
Milestone. Whatever you say.
Whatever you say they are. Okay, so typically when you set your milestones, I say, what are the next 3 things you're going to work for? What does everybody like to say? Art. Okay, fine. That's your soft, fluffy one. What are you going to do that's medium, and what are you going to do that's hard? Right. So I'm looking for something that shows that you're making substantial progress. Yes.
ABET visit.
ABET visit. I will not be here. I will be visiting another school, evaluating their curriculum.
Really? Are we accredited?
I thought they were coming.
Yeah, we're accredited. Yeah. I think we're the only accredited game program in the United States.
Really? Really? That's what I thought.
Yeah, I looked into it when I was looking for colleges and this was actually.
But guess what? That'll only get you the interview. Actually, accreditation doesn't say anything about the quality of the program.
Yep.
I'm just saying, what does it say? It says that we're constantly looking at how to make the program better. You can think of it that way, right? But again, you're going to graduate from SPSU. SPSU is a wonderful school, right? It's a good school. It's going to get you a job interview. Then what's going to happen?
We're going to get that job.
It's up to you at that point. It's what you know at that point. Okay? So last thing to point out, in trying to help you out, we're going to talk next, let's see, this Wednesday on character animation, so you have a better understanding about how some of those things work. Withdraw day is that day. That's your decision. If you want to have an honest, open kind of conversation about that, I'm fine. I do not recommend or that people stay or go. That's your decision. Okay. If you'd like an opinion, though, I can give you one. Then next week, look, project time. This is to catch up. We will not be meeting next week because I have beaten you down enough at this point that it's time to start kind of building things back together. No, but I mean, you get it. Okay, so use that time. Send me emails.
What are your office hours?
My office hours are posted on the site, but it's Monday and Wednesday for the most part. Email beforehand if you need. If you need to do something on Skype too, I can be on Skype.
My midterm grade actually isn't on there.
Send me an email then. Okay. Are you a graduate student?
Yeah.
Maybe I forgot to post it.
It was online, right?
Yeah, if it was online, you should have it.
Okay. God, how do we escape?
Plan me a waypoint. In that case, yeah. Just send me an email. Give me 2 seconds.
Go away.